of the only two formulas that I really want you to memorize from your discrete math class. One of them we already talked about is 1 plus 2 plus 3 plus 4 up to 1,000, or to any bound end. And we talked about the sum. We sort of saw that sum, we wrote it as using the Greek capital sigma summation notation. We saw there was number of terms, half the number of terms times the first plus the last term. I'll see in a moment why I phrase it like that. N halves first plus last. That's the exact answer. Really, in computer science, the thing I want to have you to have on the tip of your tongue, the tip of your brain, is it's 1/2 n squared. That should be there, just as a default knee-jerk reaction. Some of that 1 plus 2 plus 3 up to n, half n squared, which is big theta of n squared, of course. Okay, so that's good to know. What if you have a sum that doesn't quite go exactly like that? That does not 1 plus 2 plus 3 plus 4, but maybe it increments by 3 each time. Maybe it doesn't start at 1. So this video here, we're going to go through and work out this sum using only the one sum that we already know, okay? So you're not going to have to memorize any new formula. We're just going to take this summation and wrangle it around, rewrite it, do some juggling, and see that really, oh, this is that first sum in disguise. Okay, but like I say, we have a couple of problems. The first one is that our formula needs to have something that increments by 1, and this increments by 3. Oh, okay. And by the way, I'll point out that the sum here, here's Python for that big capital sigma. Just think of the capital sigma as a very concise programming language. In fact, you can think of math as a declarative programming language, maybe the ultimate declarative programming language, who knows. Okay, so we have a sum so far variable that we start initialized to 0, whatever. We go through a loop. I starts at 62, goes up through this index, through 362, or up to that plus 1. And we increment by 3. This happens to be valid Python. Great. And every time through, we increment our sum so far by I. Okay, but I want to have an index that goes up by 1. Here's what I can do. If I have an index that just goes up by 1, I can do the same thing, but I'm not going to, I'll call the index j, and it gets incremented just by 1, not by 3. But I'm going to add on, wherever I was here, where I was adding on I, I'm going to add on, not j, but 3 times j. So as j goes up by 1, 3 times j goes up by 3s. So hey, okay, I can go ahead and rewrite this. So here's our key insight. I can go ahead and rewrite this loop as saying, hey, I have a loop that goes from 20 up through 120, just incrementing by 1. Python, I don't write the step as the default is 1, so I won't bother writing it. And I'll say, yeah, add on 3 times j every time through the loop. Except, I guess I wanted to make sure it was, how do I make sure it's the right, I wanted to start with 62 because the first time I added, oh, okay, I'll take 62 divided by 3, that's 20, but with 2 left over. Okay, I'll j start at 20, and I'll add 3 times j plus 2. Then j will become 21, and this will become 3. So it started when j was 20, we had 3 times 20 plus 2. Oh yeah, 62, that was our first term. When j becomes 2, this is, oh yeah, okay. When j is 21, then 3 times 21, 63 plus 2 is 65. When j is 22, we get 68. Okay, yeah, so taking 3 times j, and then I need to figure out, oh, it's this plus 2 here, but great. And now my index is going up by 1. And now we're closer to being able to use the one formula we memorized, because we want to not memorize too many formulas. Heaven help us. But we also need to have it start from 1. So there's a similar trick we're going to use. I could have j that starts at 20 and increments by 1, and then I'll do something with j. Or I could have k that starts not at 20, it starts at 1. But wherever I use the index, I won't use k. I'll use k plus 19, because that's what j would have been. So yeah, I'm going to go ahead and have a same thing here. I'm going to say instead of going from 20 up through 120, I'm going to go through 1 through 100. So, Yeah, and we get sum so far as 3 times, and I'll take k plus 19. So when k is 1, yeah, this will be 20, and I'll 3 times 20 plus 1. When k is 2, yeah, okay. The very last term that I do add is k is 100, is that right? So I think I wanted to go one more on this. 120 minus 20 plus 1 to find the difference. And then plus 1 for Python's loop. Okay. Yeah, so I should fix that, but because there's 101 terms. That's the inside, the 101 terms. So this is 1 comma 101 is how many terms I want to add up. And again, this plus 1 is because Python doesn't include the last index as a half-open interval that Python iterates over, just like Java substring indices are half-open intervals. And it's the right way to divide intervals. Okay, great. So these are the two tricks we're going to use in math. I've given them in Python here, if actual runnable code helps you. But we're going to apply this trick to turn this into something that looks like 1 plus 2 plus 3 plus 4 up through n. Okay, so let's go ahead and try that. So here is our sum. And first I'm going to give this in two ways. This left-hand column here is a bunch of equalities using plus dot dot dot. And if you want to do it that way and write it that way in your homeworks, great, if that makes good sense to you. Here I've given on the right hand the exact same steps written in the math notation. Don't be intimidated by the math notation. If you ever are looking at something and don't know what it means, turn it into, go in your head and expand it out, or expand it out on the edge of your paper or something like that. When you're doing the homework, you can use either the left-hand column approach or the right-hand column approach, but be able to understand the right-hand column approach, okay? I might give some expressions like this and say, what's the reasoning to go from one step to another? Why? You'll go in a textbook, you'll look up on Wikipedia, whatever. People use the summation sign all over the place and expect you to know how to deal with it. And it's not that bad. So this will be some practice in doing that. So 62 plus 65 plus 68, going to rewrite that so we have something incrementing by 1. So that was 3 times 20 plus 2, 3 times 21 plus 2, 3 times 22 plus 2, and so on, ending at 3 times 120 plus 2. Okay, and you can see that that's the exact same thing here. And now once I've written like that, I can say, hey, this is in the sigma notation. At least I can now write it down. As I goes from 20 through 120, it's 3i plus 2. That's our general term. Great, let's add those up. So first of all, except I want a summation that starts from 1. So how do I do that? Well, that's the other thing we talked about. I'm going to turn, instead of thinking of this as 20, I'm going to think of it as 1 plus 19. 2 plus 19, 3 plus 19, 100 plus 19, 101 plus 19. So yeah, I've just written that out here. That's literally the same thing. Great, and I can write that using this sigma notation. Let's look at that. Yeah, I renamed it to j. J goes from 1 to 101, and what I'm adding up is j plus 19. But now I have a sum that looks like 1 up through a upper bound. Looks like we're on track for getting our formula. Of course, the thing inside here is not just j, but it turns out the only thing that's not j in here is going to be constant factors and constant additive amounts. So we're going to take care of that. If you look at the summing on the right-hand side here, 3 times j plus 19, well, that's just 3 times j plus 3 times 19, and then the plus 2 gets carried along. Again, you can think of that out here. You know, this term here, 3 times 2 plus 19 plus 2, well, that's 3 times 2 plus 3 times 19 plus 2. And the 3 in bold are the things that are incrementing 1, 2, 3, 4, 100, 101. Okay, so yeah, redo it, all that. And now if I look at this, so it's the sum, it's 101, this left-hand side is 101 things that each look like that for a particular value of j. Hey, 3 times 19 plus 1, I can do that. 3 times 19, that's almost 3 times 20, that's 60, so it's 57. 3 times 19 is 57. Plus 2 is 59. Okay, so plus 59. Great. I'm taking this really one small step at a time. That's fine. Yeah, so this, 3 times 3 plus 3 times 19, that's 3 times 3 plus 59. And the second one was 3 times 2 plus 59. 3 times 1 plus 59. Okay, so that's what we got. Okay, No problem. Math, whew, is commutative. I can add in either order. A plus B is B plus A. I'm not worried about the parentheses here. So yeah, I can go ahead and, sorry, it's associative, which means I can move it around. I said that wrong. Associative, I can ignore the parentheses. Commutative, they can commute back and forth. So yeah, if I want to add up all these numbers, I don't need to add up the 59 right away at the beginning. I can add up all the 59s at the end. I can do all the 3 times somethings first. So yeah, if I were doing something plus dot dot dot, I'd say, hey, let me say it's going to be 3 times 1, and the 3 times 2, and the 3 times 3, grab all those, the 3 times 100. And then the plus 59, plus 59, plus 59, plus 59, I'll put them all at the end. How many of those do I have? Yeah, I had 101 terms here, so there's 101 of these. What is 59 plus 59 plus 59 plus 59? 101 times? Yeah, that's not bad. That's 59 times 101. I'll write it, though, just to be super small step and complete. This thing here, the 59 plus 59 plus 59, I'm going to write that as a Greek letter sigma summation. Yeah, that's as j goes from 1 to 101, add on 59 to my counter. The thing I'm adding on doesn't even depend on j. Again, kind of silly. We know that that's just going to be 59 times 101 because I'm adding that up every time through. Okay, so yeah, great. Now we're looking on track. Now we get a sum that looks pretty tame here. And even 59 times 101, I can do that in my head, right? By dumb luck, I chose 101 because that is easy to multiply by. At least for 2-digit numbers. It's 5900 plus one more 59. So it's 5959. Okay. Look at the sigma notation. I'm going to pull the 3 out across that sigma. Am I allowed to do that? Are you allowed to pull something out of a sigma? It turns out constants. If it's a constant, I can pull it out. I can move it across. Why? I'm factoring out the 3. Think what's happening over here. I had 3 times 1 plus 3 times 2 plus 3 times 3, blah, blah, blah. I'm just pulling out that factor of 3. And I get 3 times 1 plus 2 plus 3 plus, up through 101. That's what I'm looking for. I know how to handle that. That's our one formula we memorized. So now we can go ahead and apply it. I'm going to have 3 times that sum plus 59, 59. What is that sum? Could you remember? Pause the video. Go back to the very beginning of the video where he showed the formula at the top of the page. N halves first plus last. And as there's 101 terms, 101 halves first plus last. Okay, so that's what we get. And now from here on out, we're just doing arithmetic. So let's just look at this term here. So gosh, 101 times, that's not even. Oh, 101 plus 1, that's even. Whew, I can divide by 2. So 51. 101 times 53 times 101 times 51. Okay, plus that 59, 59. 51 times 101, that's 51, 51. Okay. 3 times 51, 51. We can actually do that in our head, right? I mean, you have to stretch your brain a little bit, but it's not that hard. It's 15,000 plus another 300 plus another 150 plus another 3. Yeah, so 15,453 plus 59, 59. And now we can add, 9. We can add that in our heads. 9 plus 3 is going to be a 2, carry the 1, 5 plus 5, with that 1 carried is 11, so it's going to be 1, something 1, 2, carrying a 1, 4 and 9 is 13, 40, okay, with a 4 as the next digit, yeah, we're going to get 21, 4, 1, 2. And without a calculator, we can go ahead and using our one sum we memorized, we can find out the exact result of some wacky sum that we were asked to do. Again, it's an arithmetic sequence. Every term is equally spaced from the next. Okay, but yeah, if you get anything like that, you can go ahead and use the one formula we know and get the answer. I will sort of give away something now a little bit. I'll say that, first of all, you might say, gosh, I could probably do this I could stick in variables. Instead of saying that it goes by 3, I could say it goes up by, and I can name make an algebra constant, call it, m. Say, hey, the increment factor is m, and I have n terms, and I have a sub 0 as the first term. And you could probably come up with a formula for it. In fact, if you go back and look in your pre-algebra book, I'll bet they had a formula for the sum of the arithmetic series. I don't really need to know it if I remember that one formula. But Now here's the thing. This sum that we just got, here's another, it turns out it's the same as this, which is the number of terms, 101, times first plus last divided by 2. N halves first plus last. Yeah, that's my phrasing. It turns out that's the formula for a general arithmetic series. N halves, the number of half the number of terms, times the first term plus the last term. And yeah, this is a special case of that formula. N halves first plus last, or n terms, and the first term was 1, and the last term was n. Yeah. So why is that the sum of a arithmetic series? Is there some explanation? Yeah. What is the average term? It turns out 62, the first term plus the last term divided by 2, that's the average of the first and last term. But since the terms are equally spaced, that's also the average of the same as the second term and the second to last term, and the third term and the third to last. Those are going to have the same averages. In fact, the average of the whole sequence is the first term plus the last term divided by 2. That's the average value across the entire sequence. So if that's the average, and I have 101 of them, or n of them, what's my total? Oh, n times the average. That's what average means, right? So, yeah, n halves first plus last. I phrase it like that because it turns out that works for any formula. But if push comes to shove and I need to show that, I can say, hey, I'm going to do some algebra here and wrangle the series back into the one formula that I know that we showed previously. Okay, enjoy the homework.